All right, let's complete this SI sheet. So as usual, for the rest of the semester, I'll have some questions to prepare you for the final exam, including these two. So let's get started with those ones. First one, predict the major product of the following transformation. So I'm going to rewrite the molecule. So we're starting with an alkyne, and the first group we react it with is NaNH2. So NaNH2 is a pretty strong base. So what it's going to do is it's going to deprotonate the alkyne. If you remember from last semester, this is how you create the negative charge on the alkyne. This is the first step. The first step specifically also to create carbon-carbon bonds. So that's what we're going to do in this reaction, is we're going to create carbon-carbon bonds. So now we deprotonate the alkyne. Now we're reacting it with a methyl bromide. So I guess I'll just write out what it looks like. I'll write out the formula, I should say. So here we're going to perform an SN2 reaction. We know that because we have a strong, oh, not S2, SN2. We have a strong nucleophile right here. Strong nucleophile. And then we have a good leaving group in bromine. Good leaving group. And then in order to do SN2, remember, we can't do SN2 in tertiary carbons. We don't have a tertiary carbon. We don't have to worry about that. We have a methyl carbon, not even a primary, because it's not attached to any, any other carbons. So methyl and primary are always going to prefer SN2 over SN1. So this alkyne is going to act as a nucleophile and kick off the bromine, which is a good leaving group. So we add a methyl onto this carbon. And let me number the carbons. 1, 2, 3, 1, 2, 3, and this is 4. This is carbon 4. So 1, 2, 3, 4. All right, so that's that step. Now the next is we're using this mercury group with water and sulfuric acid. And if you remember, this is an alkyne reaction from first semester that's going to create a ketone. And it's going to, so 1, 2, 3, 4. Oh, that's 5. It's going to create a ketone on a part of an alkyne. So I chose carbon 2. You could have also put it on carbon 3, but that's what it's going to do. It's going to create a ketone. So based on that, this should be option A. What I drew is just kind of a flipped version, but that's okay. All right, next one. What reaction is best suited for the preparation of the ether? So what that means is we have to synthesize this molecule right here. So we got to see which reaction of these is going to create this. So let's look at the first one. First one, we have a bromine on a tertiary carbon. And we have a strong nucleophile. Now, remember, we can't do SN2 on a tertiary carbon. And this molecule right here is strong. So if it can't do SN2, what it's going to do is it's going to act as a base. And it's going to do an E2 and kick that off. So what that's going to create is this molecule. It's going to do an E2 reaction. So it can't be the first one, because we want to do a substitution to put this group on, not E2. So that's not going to work. All right, next one, we have magnesium bromide. If you remember from, this is actually from this semester, this is also a strong nucleophile. So it can do a SN2, but the problem is, one, we have a tertiary carbon. So we can't even do SN2. We have a bad leaving group also, so this isn't going to want to leave. And anytime you have a Grignard or organolithium with an acidic proton, it's going to take the proton. And what this is going to create is it's going to create this. And then this is going to be deprotonated like that. So it's not going to be B either. Next one, we have tert butoxide, which is also a strong nucleophile as well. And we have a primary leaving group, or we have a leaving group that's on a primary carbon. And remember, if you remember, primary carbons almost exclusively do SN2, and we have a strong nucleophile that wants to do SN2. So it's going to be C in this case. We have a primary leaving group, or a leaving group that's on a primary carbon. Primary leaving groups on primary carbons are almost exclusively going to do SN2. We have a strong nucleophile that wants to do SN2 or E2. And then because it's primary, it's going to be SN2. Let's look at the last one just to see maybe if this could be an option or why it couldn't be. So it's for the same reason above for B. If we have a Grignard with an acidic proton, it's just going to take the proton like that. So can't be that one. It's going to be C. Let me write just primary carbon. So it's this one because we have a primary leaving group. And then let me do this in a different color. And we have a strong nucleophile. Okay. That's it for the test review. Or final exam review. A and C. Oh. Hopefully that didn't mess up everything. Let me just undo. Okay, next one. We need to show mechanisms. This one is an intramolecular aldol reaction. So let's just first number the carbons. I'm numbering from top to bottom. You could, or from bottom to top, I should say. You can number from top to bottom as well. If you number starting from the bottom, Dr. Mullins would call that a Drake numbering. See if you can figure out why. Let's number these now. So I'm putting this as carbon 1 because it's an aldehyde. We have an aldehyde on carbon 1. So that means this has to be carbon 2. Now we have to decide whether this is carbon 3 or this is carbon 3. And a good way to go about that is count hydrogens. This has 2 hydrogens. And this has 1 hydrogen. On carbon 2 is 2 hydrogens. Or carbon 2. We're trying to figure out this is carbon 3. Carbon 3 has 2 hydrogens. Oopsies. And what you might find is carbon 2 is going to act as a nucleophile, and it's going to attack carbon 6. So one of these carbons here has to be carbon 3, and the other one has to be carbon 6. If we go on carbon 6 has 1 hydrogen, so and this carbon here has 1 hydrogen. So this one below is probably carbon 6. And because carbon 3 has 2 hydrogens here, and this carbon has 2 hydrogens, this is probably carbon 3. Let's at least number it like this for now, and we can always go in later and see if it checks out. So 6 is attached to 5, and then 5 is attached to 4, and then 4 is attached to 3. So this numbering works out. All right. Let's start the reaction how we normally start it. In the aldol, we're going to deprotonate the alpha carbon. So that's what we're going to do. Deprotonate the alpha carbon using our base, and then form our enolate. Oop, bad arrow. And let's show the result of this. And it's going to, I don't think I'm missing any carbons, but I'll number just to confirm. Let me use my numbering color, purple. 1, 2, 3, 4, 5, 6. Yep. We numbered the number of carbons correctly. So we need to form a bond between carbons 2 and 6, and we have an enolate, so we have a strong nucleophile. So oxygen can kick its electrons down, and carbon 2 can attack carbon 6 and then push the electrons onto the carbonyl, oxygen. So this is going to form our ring. Let's draw it out. And then I'm going to number the carbons. 1, 2, 3, 4, 5, 6. And then on carbon 6, we're going to have an oxygen with a negative charge. So this oxygen with a negative charge and water is just going to get protonated. So let's pronate it to get rid of our negative charge. So now we have a hydroxyl group. So this is where the reaction would stop if we, what do you call it, didn't include heat, but we have heat, so we have to continue. And what heat's going to do is eliminate this, and then form a double bond instead. So let's do that. So let me number the carbons first so I can show you what we're going to do next. So if you look at carbon 2 here, carbon 2 has 1 hydrogen, and in the product, carbon 2 is 0 hydrogens. So we're going to need to deprotonate that alpha hydrogen. So we'll take OH minus. We just made OH minus here. So we can use that to deprotonate. Do that. Show the hydrogen in black. And then we're going to reform an enolate. Move this up here. Now we have hydroxyl. I'm going to draw it coming up. An enolate. So now the next step is let's get rid of this hydroxyl group and move the alkene down here. Because we're in basic conditions, it's okay that OH just leaves, even though it's a poor leaving group. It's better than protonating this, because if we protonate this, that put a positive charge on the hydroxyl group, but we're in basic conditions, so we cannot do that. We know we're in basic conditions because of a NaOH, negative charge. So this will get us to the product then. And that's it for that mechanism. Okay, next one, we are doing a Claisen reaction. If you're going to take topics in an organic chemistry with Dr. Mullins, the Claisen reaction comes up, so it's good to learn it now and try to memorize it if you're going to take that class with it. So we are in the enolate chapter, so always the first step is deprotonate the alpha hydrogen to form an enolate. And push the electrons onto the carbonyl oxygen. And let's draw out what this is going to create. We're going to get a negative charge on the oxygen and form an alkene. So if you look at our products, we only want one ester, and then we want to form a ketone. So what we're going to do here now is we know that this is going to be this because this is an ester, and we're not going to have the electrons kick down and kick out this leaving group. Instead, we're going to have this enolate act as a nucleophile and attack another ester. Because we have an enolate, enolate's a strong nucleophile, so we're going to drop the electrons down, and then this carbon is going to attack that carbonyl and push the electrons onto the oxygen. And let's draw the result of this. And now in this step, I'm going to start numbering carbons. I know I didn't in the previous, but I will. Starting at this one. So this oxygen is a negative charge, and let's number the carbons. So carbon 1, 2, 3, 4. Carbon 1, 2, 3, 4. This carbon is carbon 1, and this is carbon 2. And then that must mean that this is carbon 3, and this is carbon 4. So you'll see we can get to the products really easily right here. All oxygen has to do is kick its electrons down and then kick off the methoxy group. And yes, this is a poor leaving group, but we're in basic conditions, so we can't protonate this to make it a better leaving group because that'd create a positive charge. We're in basic conditions, can't create a positive charge. So we're going to do this. And what this is then going to form is it's going to form our product. I'll explain why I'm not just doing an arrow to the product. And that is when we form this product here, we have to show one more, at least one more step. It's actually more than one. That's why I hesitate a little bit. And that is that this hydrogen right here is very acidic because it's in between two carbonyls. So when this gets deprotonated and there's a negative charge here, it's actually a pretty stable negative charge because it can do resonance twice. If you have a pretty stable conjugate base, then you're going to have an acidic proton. So because we have an acidic proton and a methoxide with a negative charge, methoxide is going to deprotonate this hydrogen, and then we're going to form an enolate. Form another enolate. Oop. And then now to get to the products, all we need to do is just protonate this oxygen right here. I didn't say that there's water. All I said was solvent, so I'm just going to protonate with water here. And that gets us to the products. So although we did form the product in this step right here, we have to deprotonate the alpha proton, reform the enolate, and then we can protonate the carbon to get to the product. I know this part here feels really redundant, but it does occur. And the reason we know it occurs is because this pKa right here is about 11. And then the pKa of what we form after this protonates, which looks like this, is about 16. So because this has a higher number than this hydrogen, that's also saying that this is more acidic than this. We know that this is going to deprotonate the acidic hydrogen. And that's a concept we learned from last semester. If you want to go more in depth or learn about that, let me know. It's not too hard of an explanation, but that would take another minute. So let's move on. So is this another mechanism? And that is sometimes the aldol reaction is always in equilibrium, or I shouldn't say it's always in equilibrium. If you're using LDA, then the whole reaction isn't in equilibrium. But if you're using a base like sodium hydroxide, then the reaction's in equilibrium. So because of that, sometimes your aldol product in the aldol reaction is going to convert back to the starting material. So we have to show that. So let's number the carbons. I gave you a deuterium, which should help you determine where the carbons are. So I'm going to start numbering at the deuterium. 1, 2, 3, 4, and then this is carbon 5. So you'll see, to get from where we start to where we end, we need to break the bond between carbons, let's see, 2 and 5. Carbon 2 in the products has 2 hydrogens. Let me use a different color. Has 2 hydrogens. And in the starting material, I guess technically in this case, it has 1 hydrogen. So we need to break the bonds between carbon 2 and 5, and we need to protonate carbon 2 as well. And then carbon 5, instead of there being an alcohol group, it needs to get converted to a carbonyl. So let's get the reaction started. So what's going to happen first is you kind of want to do the reverse of how everything occurs. So normally when you're doing an aldol reaction, let's scroll up. When you form your ring or your carbon-carbon bond, you get a negative charge, and then you protonate the oxygens with a negative charge to create the alcohol. So this is what we're gonna do the reverse of this first, because this is what occurs last in the forward direction. So what we're gonna do is, in the forward direction, the last step to form this is to protonate this. So in the reverse direction, the reverse is going to be first. Instead of protonating the alcohol, we're going to deprotonate the alcohol. And let's draw the result of that. So now we get oxygen with a negative charge. So now we got to figure out what to do. So this oxygen with a negative charge, we have to solve for the negative charge. So normally, if we have a negative charge, we can just do an acid quench and take a proton. But if we did that, that would just send us that way. So that's not going to help. So what's another way to solve for the negative charge? Well, really, the only way is to form a bond. And if we're not forming a bond with a hydrogen, then we can maybe form a carbonyl. However, if we form the carbonyl, then this carbon is going to have too many bonds. So it's going to have to break one. And which one is it going to break? Well, remember, we wanted to break, let me number the carbons. We wanted to break the 2,5 carbon bond anyways. So let's break it in this step. And let's push the electrons to form an enolate. So now this is going to create something that looks like where we want to end up. So we just formed the carbonyl. And we broke this carbonyl and formed an enolate. Like this. So we can get directly to the products now in one step. And that is we need to form a carbonyl. And at the same time, remember, this is carbon 2. Carbon 2 currently has 1 electron. This carbon here. Carbon 2 is 1 electron, but it needs 2. So with our enolate, we can protonate carbon 2. And that will take us to the product. Like that. So we just did an aldol reaction in the reverse direction. So if you wanted to go from this to, if you wanted to go from this right molecule to the left, then you just do the reverse of everything. So these are in equilibrium. All right, so that's that one. Why might the product on the left go back? Well, the main reason it's going to go back is if it's not stable. But the question is then why is this unstable? If you look at the molecule, does anything look bad or like unstable? And anytime you see a 3-membered ring, you should think unstable. So it's a 3-membered ring. 3-membered rings have a lot of strain, steric strain specifically. So 3-member ring, lots of strain. So that's the reason that the product on the left likely didn't stay. All right, now we got to predict the products. The first one, well, these are all enolate reactions. The first one's with LDA, though. So if you remember, LDA is going to take an alpha proton, and then it's going to form the enolate. And then when we've had the enolate formed, the enolate can act as a nucleophile and attack our aldehyde. And then that's going to, let's kind of draw what that's going to look like. I need to make sure I number the carbons correctly. What that's going to create is an oxygen with a negative charge, forming a carbon-carbon bond. And then we have an acid quench to turn this into an alcohol. So, and we form a new Kawel center, so racemic. So, just a standard enolate reaction. Let me number the carbons really quick, just to maybe help you out, if that helps. 9, 10. So we're forming a bond between 2 and 7. You could have also formed a bond between 6 and 7. That probably would have made more sense, but too late now. All right. There we go. All right, next one. We're doing intramolecular aldol reaction here. Let me number the carbons. So here in the first step, you'll see that there are 2 alpha protons that can be deprotonated. And it's the same on the other side. But since it's a symmetrical molecule, doesn't matter too much. However, it's going to matter whether you protonate from the, yeah, undo that. It's gonna matter whether you protonate from the secondary carbon here or the primary carbon. And let's look at what both products would be and then decide which one it's gonna be. So if you deprotonate from carbon 8, it's going to form an enolate, and then carbon 8 is going to attack. Why did I do these in red? I use red for electron movement. Okay, so you're going to form an enolate on carbon 8, and then 8 is going to attack 2. And let's draw what would happen if 8 attacked 2. So if 8 attacked 2, there are 1, 2, 3, 4, 5, 6, 7 carbons between 2 and 8. So that would form a 7-membered ring. I hate drawing 7-membered rings. For that reason alone, I wouldn't want to attack that or deprotonate carbon 8. But let's just draw what would happen if we did that. I feel like I'm drawing something wrong. Oh, no, we're good. Okay, let's just number the carbons. So this is carbon 7, 8. So then this is 8 attacked 2. It's attached to 3, 4, 5, 6. And then we have carbon 1, and then that would be turned into an alcohol. So if we deprotonated carbon 8 or the hydrogen on carbon 8 and then formed an enolate and that attacked, we would form a 7-membered ring. 7-mem ring. Let's look at if we did the other side. If we deprotonated carbon or the hydrogen on carbon 6. So that'd form an enolate on carbon 6 and 7. And then so then carbon 6 would act as a nucleophile and attack carbon 2. And there are 1, 2, 3, 4, 5 carbons in between carbon 2 and carbon 6. So that would form a 5-member ring, which is way easier to draw. And for that reason, I would prefer to deprotonate for carbon 6. But fortunately, ease of drawing isn't the determinant of what product is formed, unfortunately. So let's draw out all the carbons. So on carbon 7, what do I feel like? Oh, yeah, there's something wrong. This is going to be carbon 7 here. This is going to be carbon 7 because this is 8. This is 6. 6 attached 2, 3, 4, 5. So carbon 2 is going to methyl and then eventually protonated. So this is a 5-membered ring. So I don't know if you learned this. I don't even know. I feel like it has to be in the book. But the best rings, the most stable rings are the 5. I'm gonna write this. The most stable rings are the 5 and 6-membered rings. 5 and 6. And that has to do with the bond angles in the 5 and 6-membered rings. And 6-membered rings, the bond angles are 120 degrees. I don't remember exactly what the bond angles are in carbon 5. I know it's a little less, maybe like 117. But it has to do with the bond angles, less strain for the carbons. So that's why the 5 and 6-membered rings are the most stable. So based on that, I'm sure you can then guess that this is the one that forms, and then this is not formed. So that's not formed. We're deprotonating on carbon 6. Let me maybe I'll do that afterwards. Okay, next one. This is a Claisen. So a Claisen, if you remember, it's gonna form a ketone and keep one of the esters. So we're gonna use 2 versions of the starting material to get to our product. So I'm gonna just draw out 2 and then number them. 3, let's call this 4, and 5. So you remember when were you doing the Claisen? We're gonna form carbonyls that are one carbon in between each other. And then on one side, it's gonna be a ketone. So this is the ketone. And then on the other side, we're gonna keep the what do you call it? Oh, I just realized. That shouldn't be an isopropyl. And then on the other side, we're gonna keep the ester. So I'll have the top one be the ester. So this is carbon 2, this is carbon 1, this is carbon 3, and then this is carbon 4 and carbon 5. So desclazin is going to create a ketone and an ester, almost right next to each other, one carbon in between them, and that's aclazin. So if you have any questions on anything, let me know, and if not, then good luck on your test. Oh wait, yeah, I forgot your test isn't on Friday. Never mind. Let me know if you have any questions.